Welcome to this explainer. Okay, jump right in, and picture this with me. A packed university computer lab. Dozens of stressed-out students are frantically trying to print their term papers at the exact same time. Now imagine the absolute chaos if every single computer in that lab tried to independently control the one single physical printer. You'd have pages printing completely out of order, error messages going off like fireworks, and a printer that probably just jams and gives up on life. That exact scenario is why we're diving into the Singleton Design Pattern today. It is a brilliant architectural fix for creating one, and strictly only one, object.
We're going to move fast, so here is our roadmap. 1. The multiple object problem. 2. Defining the Singleton pattern. 3. Writing Singleton in Java. 4. Pros, cons, and trade-offs. And 5. Extending to the Multiton. Let's get into it.
Section 1. The multiple object problem. Because honestly, to really appreciate the solution, we kind of need to feel the pain of the problem first.
So, ask yourself this. What actually happens when every single computer decides to create its own totally independent printer manager? In object-oriented programming, we're taught to just spin up objects whenever we need to model something, right? But is more always better? Let's see what happens when every isolated piece of code decides it deserves its own dedicated manager for a single shared resource.
Let's look at our university setup. You've got Lab A, Lab B, the library, and the staff room. In a naive software design, each of these modules is instantiating completely separate printer manager objects. But here's the catch. There is only one physical printer server. It's literally like having 4 steering wheels hooked up to the same car, with 4 drivers aggressively trying to turn at the exact same time.
And yeah, you guessed it, it's a complete disaster. We aren't just talking about a minor little bug here. We're talking conflicting print jobs where page 1 of a student's essay prints out right before a random payroll sheet. Because each manager has its own separate queue, the hardware just completely loses its mind. You get inconsistent statuses, and from a systems perspective, spinning up all these duplicate objects means we are just hemorrhaging memory. It's wildly inefficient.
All right, Section 2, defining the Singleton pattern. Time to introduce the hero that's going to save us from all this systemic chaos.
Enter the Singleton pattern. It does exactly what it says on the tin. It strictly restricts a class to have one and only one object, and it provides a global access point to get to it. This elegant little solution guarantees that no matter how many times a module in your system begs for a manager, only one instance is ever going to exist. You are basically putting a single, very strict bouncer right at the door.
To put this into perspective, think about real-world scenarios where having multiple bosses would be an absolute nightmare. A school only has one principal, right? If there's an issue, everybody goes to the exact same person. Or a national ID database, that absolutely has to be a single source of truth to keep citizen records consistent. And oh man, air traffic control? You 100% need one unified system managing those flights, or things go terribly, horribly wrong.
Which brings us to Section 3, writing singletons in Java. Let's look under the hood and see how we actually prevent other developers from just spamming the new keyword.
The absolute secret sauce of this implementation is a private constructor. By making the constructor private, we completely lock down the ability for anyone outside the class to just type new singleton. They literally aren't allowed to do it. Then we pair that with a private static variable called instance. Now, because it's static, it belongs to the class itself, not to any individual object. That ensures there is exactly one slot in memory holding our precious object. So if nobody can use the new keyword, how do we actually get the object? Well, we use a public method, usually called getInstance. And the logic inside is so simple but so brilliant. Step 1, it checks, is the instance variable null? Meaning, has the object been created yet? Step 2, if it is null, it uses that private constructor internally to build it. Step 3, it hands it back. But the real magic happens the next time you call it. The instance isn't null anymore, right? So it entirely skips the creation step and hands back that exact same object it made the first time.
And here is the proof. If we ask for singleton S1, and then on the very next line ask for singleton S2, what actually happens in memory? Well, if we check if S1 equals S2 using the double equals operator, it evaluates to true. Remember, in Java, double equals checks if 2 references point to the exact same memory location. Because that second call just handed back the first object, S1 and S2 are identical twins. They are pointing to the exact same spot in memory.
Section 4, pros, cons, and trade-offs. We've seen how powerful this is, but we all know in software engineering there are no silver bullets. Let's weigh this out.
On the plus side, it is a massive memory saver because you aren't needlessly spinning up hundreds of objects. You get totally centralized control over a shared resource, and the access is incredibly easy. But there's a catch. Singletons introduce really tight coupling. Since any part of your code can just yell get instance out of nowhere, you end up with these sneaky hidden dependencies scattered all over your project. Good luck unit testing that because you can't easily isolate parts of your code. If you get lazy and overuse it, your singleton just becomes a glorified global variable trap, making everything rigid and super hard to maintain.
But despite the haters, you are going to see this pattern literally everywhere because it solves specific problems perfectly. Database connection managers use it to efficiently pool connections. Video games use it for settings, so your audio volume stays the exact same across every single level. You'll also see it in software drivers talking to hardware, building automation systems controlling the AC, and massive payroll processing systems where duplicate calculations would be, well, a financial disaster.
Finally, Section 5, extending to the multiton. What happens when you need strict control, but one single instance just isn't going to cut it?
What if our university lab actually upgrades and gets 3 physical printers? Well, we adapt. The Multiton pattern tweaks our singleton logic to maintain a fixed collection of instances. Instead of one single instance variable, we use a list capped at a maximum number, let's say 3. When a module wants a manager, the Multiton hands one out using a round-robin cycle. Call 1 gets printer 1, call 2 gets printer 2, and so on. It's the exact same safety net and resource management as the singleton, just scaled horizontally to match the hardware.
So, I'm going to leave you with this final thought. The singleton is a remarkably clever piece of engineering to stop resource contention and memory bloat dead in its tracks. But you've got to wield this power carefully. The next time you sit down to write one, I want you to ask yourself, do you truly need a singleton to manage a shared resource? Or are you just using it as a super convenient rug to sweep your messy, hidden dependencies under? Think about it. Thanks for hanging out for this explainer, and we'll catch you next time.